Hi, my name is Michael Müller, and I'd like to show you something I've been working on and off for the last 2 years. It is called Hybrid Fortran, and it is a performance portable way of targeting CUDA as well as OpenMP in a unified code base with Fortran. Now, for this video, I'd like to show you a little bit how a hands-on experience looks like with Hybrid Fortran. I have cloned this open source directory from GitHub into my local machine. And the only thing I need to do to set it up is to set an environment variable. This is all documented, don't worry about it, but that's basically what you have to do in order to tell Hybrid Fortran where all its tools lie. Now I have a folder that looks more or less like this, and to get started what I can do is I just type make example, and this will create a new example directory, which is basically like a template for your project. This will give you some source folder with some example code to show you how it works, and a config folder that has some configuration files for the build system, as well as a make file. But this is really small. It's basically only 2 lines that reference the common make file that is in the HF directory. Okay, now let's move this into a more handy location, or maybe let's just rename it to my example Stencil project. Now I have my editor pointing to my Stencil project, and as we can see, what we get is some example source code. Let me delete everything except maybe the main program initialization, such that we can start over. Now let's write a stencil. What is that, a stencil? Well, Wikipedia has some nice illustration about what's a stencil code. It is basically a pattern for iterative codes that say that you always access the neighboring elements for the point that you are in right now in a, let's say, in a loop that is indexed in 3 dimensions. So let me write the simplest possible stencil code we can think of. Let's do a 2-dimensional stencil with 1 input and 1 output. And let's just set b at ij equals a at the same point plus a at I plus 1 j. Okay, so we just sum up a at the same point as b plus its neighbor. Now I want to quickly write the loops for you. So on the CPU we would just, in order to do the whole region, loop over this with, say, m from 1 to m, and with I we have to make sure that we don't access too much, because here in the last iteration we will have I plus 1 so we need n-1 as the iteration boundary. So this is a very simple stencil with a halo region. It's a so-called halo region of one vector at nm in the two-dimensional array. Okay, so let me quickly write the specification part, and in order to not bore you too much, I want to just skip this in the video. So now we have our stencil. I hope that this will work correctly. And as you can see, we just have a CPU implementation right now that just sequentially updates B. So let's call this, and first we have to initialize the arrays correctly. In this case, I want to make them allocatable. Usually this is the safest way to do things. And what else do we need? We need boundaries. Let's just set them to 4 and m to the same boundary, and then allocate a to n m and allocate b the same way. And never forget to also deallocate that stuff at the end. So we should be able to call this stencil now. Oh, I forgot something. Of course, I didn't initialize it. So in Fortran, I can just say the whole thing should be set to, say, 1. And for B, I want to initialize it to 0. And then at the end, we can, for example, write that stuff out to the standard error, for example. Right. And let's see what happens. Before we build this thing, we should also have a look at the build settings. Right now it should be enough to just set the executable to the same name as the H90 file that we used in the source. This way the build system will automatically pick it up and compile it the right way. Now in this case we only have Fortran code. There is no hybrid Fortran fancy stuff going on, but still we already use H90 to show you that you can always do this, and your Fortran code will simply be passed on to the compiler without change. So in order to test this, we need to first copy the code into a system that has everything that we need to build. So on my local machine, I don't have PGI compiler. For this, I'm using a compute cluster. And I just synchronized the directory up to this cluster, and let's build it here. Okay, so we have one little problem here at line 25. I see. We didn't actually make the call statement, so let's synchronize again. rsync is really a handy tool, isn't it? Okay, now we got something. Okay, what happened here is that I forgot to specify that this is actually supposed to be an array, so it didn't make it correctly an allocatable array that I can initialize afterwards. Okay, after this we can now compile it, and it has also installed the finished executables into a test directory. Let's just go there and look at what happened. Now we have two different executables, example CPU and example GPU. Now that may not make too much sense right now because we are not actually hybridizing this code yet for the GPU, but nevertheless Hybrid Fortran already creates two separate versions that are compiled with two separate compilers, once for the CPU and once for the GPU architecture. And if we run it, let's hope that it does something useful. Alright, it's maybe not so useful to write A. We should probably rather write B to see the result. Let's make install again. And as you can see, the build system of Hybrid Fortran, it basically does most of the things for you. It already picked up everything from the moment we specified example as the executable name, and when you have the same file with H90 specified, it will just work. Okay, that looks better. We have 2 in the output everywhere. Yeah, see what happens here is that it's formatted the data in the output a little bit incorrectly because we have actually a 4x4 matrix basically, but we see that the 4th value is correctly one of the halo points, and then we have the next line 3 2s and then once again a 0. So the whole thing works. And now we want to know how we could parallelize this. Now, basically what you need to do in Hybrid Fortran is, first of all, we don't want to write loops in Hybrid Fortran. The reason for this is that loops are inherently not parallelizable. Loops can have dependencies so arbitrarily that basically there is no way that a loop can always be recognized as parallelizable. And in order to simplify this whole problem a bit, we start by giving this a different name. We call this a parallel region. Now this is a Hybrid Fortran directive, and instead of looping over it, we tell the framework that this can be executed in parallel. As you see, there are only dependencies with local information, so B does not depend on anything, any updated value of B in at the further point. So we can easily parallelize this over the domain ij. And for this we specify the domain name ij. And we also need to give it a size for the domain. In this case we use the full domain size, n and m. And also we so the start that is okay like this, but we need to tell it to stop at n and n-1m, such that we don't run over the array boundaries. Okay, so now that we have written it this way, there are some things missing for the GPU, but for the CPU this should actually already work. So let me try this out. And we can do this only for the CPU if we say make install underline CPU, and then it will I see we forgot to synchronize. Yeah, so let's see what happens here. I see. I misspelled parallel region. That of course cannot work. Okay, I see. There is one more problem here. Hybrid Fortran always wants us to specify domain dependence, because it thinks, well, if there is nothing that we are actually updating and that needs to be taken care of in terms of data, then it's not really valid to have a parallel region. And we do this by using the domain dependent directive. And in this case here, so basically when we write this and we put something here, let's say A, B, this would mean A and B is scalar, and please take care of all the transformations that are needed for A and B to work on the architectures that I want to parallelize it on. In this case, A and B are not scalar, so we use an attribute called autodom, and what this does is it uses the declaration that we have already used in our portable Fortran code, and uses these same declarations also for A and B. All right, so let's see whether this works now. I also misspelled domain dependent. Right, let's try again. And so this appears to have worked. Let's look at the output. And we have the same output again. Now, let's just have a look at what this actually did in the build directory. So for this, I need to open up the mounted directory from the compute cluster. And I want to have a look at what actually happened in the build, so I can show you what Hybrid Fortran did in this case. Okay, now this is the version that has been built on the cluster. And as you can see, the source directory, it's actually not touched during the build process other than being copied into the build directory. And in the build directory, you get two different subdirectories, one for GPU and one for CPU. Then you get call graphs and preprocessed that you can ignore for now. And here we have example.f90, which interests us. And all it did in the CPU case is introducing OMP parallel directives, so we can use OMP or OpenMP in this case for parallelizing on the CPU. So nothing too fancy going on here. Let's look at what happens when we try to build this for GPU. What it did here is it created a kernel, a so-called CUDA kernel, by introducing these additional attributes here. It just initialized these indices. It returns if these indices are out of bounds that we have specified. So in this case, if I is greater than n-1, it will just return. But there is a problem here, and the problem is that this Stencil kernel, when it's being called, it's not properly called as a kernel. Because when we do this, first of all, it would not recognize these additional attributes, and also it would, even if it would recognize it, it would just run for 1 point. And also these block indices and all that stuff, that's not going to be initialized for us. So we have to tell CUDA to somehow create a kernel out of this when we call it. And what we need to do in our code is, so hybrid Fortran, one of the things you have to know is it only operates on subroutines for now. So in order to actually pick up this call here, we need to put it into a wrapper subroutine. And basically we just use the same interface here in that case, and we call this interface from the main program, and we call the kernel from here, because this way hybrid Fortran will pick up this this Stencil call, and it will properly initialize it for us for the CUDA kernel initialization stuff, basically. And we also need to tell it to be aware of A and B, such that because we want to run this on the device, it also needs to copy in and out the arrays properly for us, and it will use the intent information that you give it in the specification part. So if you use the same specification part as in the kernel, it will automatically know that A is an input, B is an output, and so it will correctly do the memory handling for us in that wrapper. So hybrid Fortran, it can handle the memory transfer for you, but it only does this at the beginning and at the end of a subroutine. So basically you specify for one subroutine what kind of symbols that it needs to be aware of, and hybrid Fortran will at the beginning of the subroutine basically initialize all the device outputs to 0. It will copy in all the inputs that need to go on the device, and at the end of the subroutine it will copy out the output for you. But we need a little bit, we need more, at least one more layer of subroutines to make this happen compared to the original program. That's basically the major migration step that we had to do. Okay. So let's sync this and let's see what happens. Okay, let's just have a quick look at the new code that has been built for the GPU. As you can see, it still looks relatively well indented and we can still read it. But now you see that in the wrapper, we did additional initializations of A and B. And we do this in order to have the stuff ready on the device memory. And also we do all the initialization stuff for the CUDA kernel and we do some error handling when the kernel comes back. So this is all well and good. Let's see what happens if we run it. Oh, it actually works. Okay, so now we have written a stencil that runs on the GPU. Of course, you should be aware that if you want your GPU code to be actually faster than your CPU code, you will need something like at least a region of, say, 128 by 128 at the least, probably even more. So you need in the order of 10 to the power of 5 threads to be able to operate on this. And the number of threads you can actually influence by changing the storage order. So I did a mistake before. I changed the F90 file, which is not a good idea, because if you build, or if you change something in a H90 file and then build again, it will delete all the changes you made to an F90. But still, sometimes it's useful for debugging purposes. So if you don't change something here, you can go in the F90 file and introduce write statements, for example, in order to see what happens more clearly. Okay. Yeah, I wanted to show you the block size. So with the CUDA block size, you steer the number of threads that you're going to have. Here it is set with the default configuration. It is set quite, let's say, conservatively, but we can usually set it to 32 by 32 quite comfortably, and this usually is a very good block size setup for CUDA. And if the memory is not enough on your GPU to handle so many threads, it is advisable to first decrease the second dimension to something like, say, 32 by 16. Okay, so so much for that. This was a quick, or rather not so quick, screencast about how to parallelize a stencil on CPU as well as GPU with a unified code base. Next time I'd like to show you how you can actually influence what is being written in your code that is to be run on the device or on the CPU. And we can go and have a look at how Hybrid Fortran enables automatic reformatting of your data, such that if you have to reformat for a particular device because with a different data format it's faster, you can still keep your code base the same way it looked before and let Hybrid Fortran do that whole tedious reformatting for you. So see you next time. I hope that you stay with us, and if you want to be informed about updates, please follow us on Twitter and subscribe to this channel. Thank you very much.